So we've been looking at sequences, series, and now we're finishing up with sigma notation. And we had previously looked at the sum of finite series and infinite series, and we did some by hand. But now we're going to use, with the help of our calculator, sigma notation. And so sigma notation is called this because the symbol that we use is the Greek uppercase letter sigma, which looks like a large E. And I'm actually going to be working from example 6. This is guided practice 6A, 6B, and 6C, which is located on page 594. And we're going to load this sigma notation in to find the sum of the series. And so I first want to go to math. And as I scroll down, and I happen to know that this is option 0, but I'm going to scroll down, I see summation, and this is the Greek letter sigma. And so I'm going to hit enter here. Now before I begin, well, I didn't mean to hit it twice. So let me get back to it. Okay. So let's talk about what these boxes represent. Now these two boxes and where you see the blinking thing there on the cursor, this is designating what the first term in the series is. And this box above the sigma is indicating for us how many of the terms we are going to sum. And then this box here on to the right of sigma is our actual formula for the sequence or the series. So in this first one we've got, and you can see that it's in alpha character, it's blinking that A. And so I just go over here, because we're going to take n, and you can use any variable, but we're going to use n since it's here, n, and then it pops here to the next box, so 1. So the first number in this series is 1. And then I'm going to hit the up arrow, up cursor, and it's going to hit the upper block, and it's going to be blinking, and I'm going to then put 5. So in other words, we're going to be summing the first 5 terms of the series, and now we're going to put in our formula, which is, in this case, n squared minus 1 divided by 2. So I'm going to go parentheses first, because I'm going to put that n squared minus 1 in parentheses. Then I'm going to hit alpha. I'm going down here to log, which is n. You can see the green n. And then I'm going to hit the square right here, n squared minus 1. I'm going to close my parentheses. I'm going to divide all of that by 2. I'm going to move my cursor beyond the furthest parentheses. I'm going to hit enter, and hopefully I'm going to get 25. And I do, 25. So if I were to plug in 1 for n squared minus 1, well, let's see, 1 squared minus 1 is 0, so that's going to be 0. That's the first number of the sequence. If I put in 2, that's going to be 4. 4 minus 3 divided by 2 is 3/2, and so on and so forth. And I add those first 5 terms up, we're going to come to 25. You can do it by hand if you'd like. Now let's do the next one, which is sigma notation n equals 7. We're going to do 13 numbers, and the formula is n cubed minus n squared. A little bit more complicated. I'm going to hit math again. And because I know this is option 0, I'm going to just hit 0. It's going to put that in. I'm going to put n. Again, it's already, the alpha is already blinking. So I'm just going to hit right at the log button, which right above that is n. And n is equal to 7. So we're starting with the 7th number in the sequence. And then we're going to go to the 13th number. So this is the sum of the 7th, 8th, 9th, 10th, 11th, 12th, and 13th number in the series. And now let's put in our formula, which is n cubed minus n squared. So I'm going to hit alpha, n, caret, 3 for cubed. I'm going to move my cursor down here. Minus, I'm going to hit alpha again to hit n again. And we're going to have the squared this time. I'm going to move the cursor beyond the parentheses. And I hope now I'm getting 7,112. Let's see. Yes, I did. I got to put in there right. 7,112. Now, you have to admit this is much easier than doing it by hand. Thank the Lord for calculators. All right, we got one last one, and this one is going out to infinity. So this is an infinite series. And, well, let's just start. I'm going to hit math. I'm going to hit option 0. I'm going to hit n equals 1. You can see this on page 594 in your textbook. Now, there is not an infinity symbol in for the TI-84 calculator. And so I may just want to pick a large number. Now, I'm going to pick one that I happen to know is going to give me an error message, because we're just going to use that to discuss. But I'm going to say, okay, well, 100 is a large number. Okay, and then my formula is 6 divided by 10 raised to the power of n. So I'm going to hit caret alpha n. Move beyond my cursor. I'm going to hit enter. And I get this nasty error message. It says overflow. Calculation exceeds the range of values this machine is able to display. So I go, okay, well, let's go to. And I'm going to go and say, well, let's see. What if I reduce that 100 to 10? So I'm going to go to math. I'm going to see if I can delete that. Is that 10? Yeah. Okay. So I fixed it where I just got to 10. Maybe that'll give me what I need. And if I think about it, I've got 10 in the denominator, and I'm raising it to a power. So 10 to the first power is 10, so that's 6 over 10 or 0.6. And then if I square 10, it's going to be 100, so that's going to then be 6 100ths. And if I cube 10, that's going to be 1,000th. So that'd be 0.006, on and on and on like that. I'm going to hit enter. And I get 0.6666, and it should probably be 10 decimal places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It takes it to the 10th decimal place of 6 repeating. So I could write that as 0.6 repeating, or you might recognize that also as a fraction, which is at 2/3. Okay. Point is when you're doing infinity, there's not a symbol. And so you just need to kind of pick a large number. Really need to think about what it is that your variable is doing. And in this case, since it's an exponent, it's going to get very large very quick. I mean, 10 to the 5th power would be what? 100,000, 1 over 100,000. 10 to the 6th power is going to be 1 over 1 million. So it'll be 1 millionth or 6 millionths in this case. So it gets to be a large number pretty quick. But there we go. We're finding sums of series using sigma notation.